the 1 certainly gets mapped to by many. Right? It's a many-to-one mapping. Now how about the -1? Well, now when you have just 2 elements in your permutation, and all the other ones are not mentioned, that means all the other ones do not change in the reordering. The only 2 that change is object number 1 and object number 2. So, well, in this case, so this length 2 cycle. So 1 and 2 just swap. 2 becomes 1, 1 becomes 2 in position. So that's called a transposition. Transposition is a cycle of length 2. So here, this 1, 2, that's a transposition. And part of the theory of lecture 12, chapter 12, was proving that a transposition is an odd permutation. Right? It's an odd permutation.
A vast virus database has been updated.
So then big N of that transposition will be odd. Okay? So if you map a transposition, you get -1 because the transposition is an odd permutation. Okay, so -1 gets mapped 2. +1 got mapped 2. Now there are only two elements in the whole group. So the mapping is surjective, right? Both those 2 elements, in other words all the elements, got mapped 2. So it's surjective. Alright. Now the image of F, what does that mean? It's all possible different values of F. Well, there are only two, right? There are only 2 possible values that F can be, F of X. So it's +1 or -1. Right? So your image is is this very small set of 1 and -1. So that's your image. That's your image. The image of F. Okay? Just the set 1 and -1. Now how about the kernel? What's the kernel of your F? So it's the set or subset of all those elements that map to the unit of your codomain, the unit of your target group, right? Right? So here's our function. So we're mapping the symmetric group to effectively C2, cyclic group order 2. Yeah, so where the set is 1 and -1. Okay, of this group, which one is the unit? Well, just 1, right? The element 1. Now, which elements in your symmetric group map to 1? So, and what does that mean? Well, here, if it's mapping to 1, it means the permutation is even. Okay? So all the even permutations are mapping to this 1. But that's the definition of the alternating group. Okay? Every member of the alternating group maps to +1. So the kernel is just the alternating group, right? Because what is the alternating group? It's all those members that map to +1. It's all those permutations of the symmetric group that are even. Okay? So the kernel is this. Alright, so we know the kernel, we know the image, there's the kernel. So we can just plug these two now into the first isomorphism theorem, and you've got your parent group, right? Your big G, if you like, which is the symmetric group, slash kernel, which is AN, kernel's AN, so put that here. And that's isomorphic to the group, that's the image of your f. And what is the image? The image of your f? Well, it's this set here. Okay, and the binary operation is multiply, so that's your group. Okay, and there it is. So we've done it. Quite a bit of thinking there, and some revision from chapter 12. So, and I've done it in fair detail because those of you going on, and I'll be talking a bit about this towards the end of this session, those of you going on to do high-level finite group theory, you will keep coming across this alternating group. It's truly famous in finite group theory, like A5, I think I've mentioned this before, but if you have 5 objects, and n is 5, that's the first non-trivial simple group. Actually now, I mean, talking about simple groups is for M1 level, that would be the next level up at grad level. But I can now tell you what a simple group is, because we've done enough theory. We're now at the end of this course. A simple group is one which has no, other than the trivial group, just E, or the group itself. So a simple group by definition is, is a non-trivial normal subgroup. Okay? If a group has no non-trivial normal subgroups, by definition it's simple. Right? Now you probably won't appreciate what the significance of that yet until the next course at M1 level, and I'll be talking about that a bit. If there are normal subgroups, you can then sort of, in a manner of speaking, break down. You can sort of factorize, in a sense, the group into smaller groups. But if you can't do that, then that group you cannot factorize it. It's sort of analogous to like a prime number. You can't break down, you can't factorize a prime number into smaller numbers, factors of smaller numbers. And similarly, with a simple group, there are no normal subgroups, therefore you cannot factorize it in a sense. You can't find quotient groups or factor groups for that group. That's as simple as it gets in a sense. You can't break it down into smaller groups, and that's what a simple group is. So now you know, right? And A5 here, the alternating group, is the first non-trivial simple group. Remember, if your group is abelian, then any subset of that group, any subgroup of that abelian group is normal. So that's sort of the easy cases. But for the non-abelian groups, which are sort of harder to deal with, the first I don't want to use the word simple. Well, let's say non-abelian group is A5. So it has historic significance. And we will prove that A5, is like, in a sense, the first non-simple, well, non-trivial, I can't use that either, non-elementary group, the first simple group of that kind. Okay, 2, quicker and a bit easier. So just to do two of the 5. You're given a function, you're mapping the non-zero, star, the non-zero complex numbers into, onto the positive reals. Okay, so you're taking a complex number, non-zero, take a complex number and map it into real numbers that are positive. So and it just says find A. So it's an open-ended question. You just have to dream up something. You have to find it yourself. So you have to find a surjective homomorphic function f, right? And then apply the isomorphism theorem to it. Well, open-ended questions are tougher because you just have to find something yourself. You're not given it in the question. You have to think of one. So well, you can probably see it here, but well, imagine you didn't have that, and so you're having to think for yourself. Let's see. So I take a complex number and I convert it into a real. So how do I do that? How do you take a complex number and make it a real? Well, one solution is just to find the absolute value of it. There may be other ways, right? You may find another way, but anyway. So a solution, you only have to find one. There may be many, maybe not. But anyway, here's one of them. Just take your complex number, non-zero complex number, and just mod it. Find the absolute value of this. Right? So now, is it homomorphic? Well, f of z1, z2, just product of two complex numbers. Using this definition is just mod of z1, z2, and you can split that up into mod of z1 times mod of z2. But mod of z1 is just f of z1. Mod of z2 is just f of z2. So f of z1, z2 equals f z1, f z2.